seen 6 already, but now we're going to see a much more interesting one. By the way, one easy point here is that I had an axiom of union, but I didn't have an axiom of intersection. So you can actually prove something like this for intersection using union and comprehension, because the intersection of a bunch of sets is a subset of their union, right? So just think about this. Think about how you can define intersection using these two, using union and comprehension. But now we're going to do something else. So remember at the beginning of this course, I talked about Peano's axioms for natural numbers. But now we're not really working with numbers anymore, we're working with sets. So in some sense, I don't like this idea. I don't like that I have a different definition of what numbers are, and now I have a bunch of axioms on sets. So let's just define the numbers. Let's give a different definition of the numbers such that every number is a set. Okay. So here's what I'm going to do. I need some sort of a set to represent the number 0. Okay. So which set should represent the number 0? Yeah, let's just say 0 is the empty set. Okay. And now suppose that I have some number n. I need to somehow define the successor of n. So n is a natural number. N is also a set because I want everything to be a set, including all of my numbers. I want to define the successor of n. Here's how I define that. I say this is n union with a set that only has n as well. Okay. So what does this mean? Let's just do some examples. So 0 is the empty set. 1 is 0 union with the set that only has 0 in it. So 1 is this set. Okay. Or, well, I can write it like this. Or I can also write it like this. Okay. So that's what 1 is. What is 2? 2 is the successor of 1, so it's going to be 1 union with the set 1. So it's just 0 and 1. The set 0 and 1 is 2. But if I want to extend this, it's a set that contains 0, and 0 is this. And it also contains 1, and 1 is this. So this is 2. Right? And I can continue like this. But generally speaking, it's very easy to see that basically whenever I talk about a number n, it's the same as the set of numbers from 0 to n minus 1. That's the intuition here. And this is a great definition because now every number n is a set with exactly n elements, right? So 2 is a set with 2 elements. I like this. And every number is just the set of all the smaller numbers, which gives me an easy way of defining, for example, comparison. So if I have two numbers n and m, what does it mean to say n is less than or equal to n? I can define this to mean that n is a subset of m, right? What does it mean for n to be strictly less than m? I can define this as meaning that n is a member of m, right? So I can do all sorts of cute things like this with my numbers now. But generally, if you look at this new definition of successor that we have here, which is very different than when we were doing Peano's axiom. When we were doing Peano's axiom, we were just saying there is a successor without actually giving any kind of construction for it. But if you look at this definition, I can apply it to any set, right? So I can now have a more general definition saying that if X is a set, then the successor of X is just defined to be X union with a set that has only one element, and that element is K. Okay, so I can now define a successor for any set. I can also define what I call an inductive set. So here's another definition. And you will see why this is called an inductive set immediately. So we say a set X, set, let's use big X, is inductive if, first of all, the empty set is a member of X, and secondly, for every set in S, so for every, let's call it Y, if Y is in X, then the successor of Y is also in X. Okay, so if I say a set is inductive, this is what I mean. I mean the empty set is in there, and for any set that is a member of X, the successor of that set is also in X. Okay, you see the connections to induction and so on, right? But, well, I mean, we haven't got to a point where we can prove this yet. And even when we do, I don't have the time for it, but the set of natural numbers n is inductive, right? You can check this. But n is not the only inductive set. You can easily create other inductive sets as well. So here's the axiom that lets you do this. And this is the first really interesting axiom. This is ZF7, which is called the axiom of infinity. Okay. And this axiom is very simple. It says there is an inductive set. So an inductive set exists. That's all this axiom says. Now, why do we call it the axiom of infinity? Because if I use all of my previous 6 axioms, I'm only working basically with finite sets, right? If you look what I'm doing here, well, this is just about equality. I'm starting with the empty set. I'm creating pairs. I'm creating unions. I'm doing comprehension, which is only creating subsets of what I already have. And I'm doing power set, which, well, wouldn't make an infinite set for me. So if I have a bunch of finite sets starting from the empty sets and just keep applying these things, I will always get finite sets. But this is a really important one because now it's giving me an infinite set. But of course, I haven't defined infinity yet. So infinity for now is just the name of the axiom. So there is an inductive set. That's what this axiom says. Okay, can I write this axiom in my language L? Yes. So it means this. It means that there exists some set X such that, well, I want it to be inductive, so it should satisfy these 2 conditions, such that the empty set is a member of X, and we've seen already how to write the empty set in our language. And for every Y, if Y is a member of X, then the successor of Y is a member of X. And of course, I can write successor in my language too. So instead of successor of Y, I can just directly plug what it means. It's Y, Y union with Y. Okay. So this is what this axiom is saying. There is an inductive set. Okay. Now, I don't just like to talk about any inductive sets. So at this point, we are after ZF7. I want to talk about the set of natural numbers, right? So I'm going to define it like this. I'm going to say there is a smallest inductive set. And I'm going to call that smallest inductive set the set of natural numbers. Okay. So what do I mean by smallest? I mean it's a set that is a subset of every other inductive set. Okay. So we have this theorem. So there is a unique set N. Of course, I'm writing it like that, such that it is contained in every inductive set. So of course, such that N itself is inductive and it's also contained in every inductive set. So such that 1, N is inductive, and 2, for every inductive X, any inductive set X, we have N is a subset. Okay. Which again, if you think of it, is very similar to what we had with Peano's axioms. So with Peano's axioms, I was saying I start with 0 whenever I have a number, I can have its successor, and I don't have anything else, right? Here, it's just saying that a set is inductive if it has 0 or the empty set in it, and whenever it has a set, it has its successor. Now I'm saying, let's look at the smallest set that has these properties. It's going to again give me the natural numbers, but I have to prove that, of course. I have to prove that there is a unique set that is inductive and a subset of every other inductive set. Okay, and of course, after I prove this, I'm just going to call it the set of natural numbers. Okay, we have to somehow construct this set using our axioms. But the only axiom I have here about infinity is that there is an inductive set, right? It doesn't tell me anything about that inductive set. It just says that there exists a set that is inductive. But that's enough, actually. So here's what I'm going to do. I say, well, there is a set that is inductive. So I say, let Y be an inductive set. Okay, I can do this because the axiom tells me that there is an inductive set. So let's call it Y. Right? Now, Y is not necessarily N. I want to somehow get N out of Y. So here's what I'm going to do. I'm going to use comprehension. So this one exists because of the axiom of infinity. But now I'm going to use the axiom of comprehension. What is the axiom of comprehension? It means that, well, I know that the set Y exists. So I can look at all the elements Y in Y that satisfy some formula in my language. Okay? Here's the formula that I want to write. I want to write this. I want to say, I want to take all the elements Y in Y such that for every set X, if X is inductive, I'm just going to write it like this, then Y is in X. Okay. Now, I can write this part, the inductivity of X in my language. I've already done this here. Right? So this is just saying that X is inductive. So this whole thing is a formula in my language. I can write this formula. And I'm doing comprehension, but I'm doing comprehension on a set that already exists because my axiom of infinity is saying that this set big Y exists. So I'm taking all the elements in the set big Y that are in every inductive set. Okay, I'm going to call this set N. Okay, so I have to prove two properties for N. I have to prove that N is inductive, and I have to prove that if I have another inductive set, then N is a subset of that inductive set. The second one is obvious, right? So if I have another inductive set X, by definition, every Y here is in X. So N is a subset of X. Okay, so this property 2 is obvious. 2 is easy. I have to now prove 1. So I have to prove that N is inductive. Okay, but proving that N is inductive is again a matter of proving two things. I have to prove that the empty set is a member of N, and I have to prove that whenever something is a member of N, its successor is also a member. Okay, first of all, the empty set is a member of Y. Why? Because Y was inductive, right? And also for every inductive X, the empty set is a member of X, right? So for every X, if X is inductive, then the empty set is a member of X. Again, this is just definition of being inductive. So now by this definition of N that I have here, this is my definition of N, I know that the empty set is in N. Okay. Now, suppose that I have some element in N, I want to show that its successor is also in N. So let's say I have some elements, let's call it N. N is in N. Okay. What does this mean? By definition, it means that for every X that is inductive, N is in X, right? But N is in X and X is inductive, so X definitely contains the successor of N, right? So for every X that is inductive, I know that the successor of N is in X. This is again just using the definition of inductivity of X. Okay, but now look at successor of N. Successor of N satisfies this property here, right? Because this is the same as this one. I just have to show that the successor of N is also in Y. But Y is also inductive. And N is in Y, so successor of N is also in Y. So now by definition, successor of N is in N. Okay, so N is inductive. So what did we prove? We proved that there is a set N such that N is inductive, and it's also a subset of every other inductive set. Now, why is this unique? Super easy. Suppose that there are two N's, N1 and N2. Then N1 is a subset of N2, N2 is a subset of N1, they're the same. Right? So it's unique. Because each of them has to be inductive and each of them has to be a subset of every inductive. Okay, great. So we finally have our natural numbers. Now we can do all the things that we did when we had Peano's axioms: addition, multiplication, division, all number theory, I don't know, comparison of numbers. And actually the books on set theory do these things, and like doing induction, proving it's the same as well ordering. We've already done all of this. So I'm just going to jump to the next one. So I'm going to give you the 8th axiom. So the remaining axioms are honestly not that interesting. I mean, they are interesting if you're doing something more advanced, but not in this course. So for the 8th axiom, I need another definition. So here's the definition. Suppose that I have a formula. So I'm saying let phi of xy be a formula in my language such that for every x, there is exactly one y that satisfies this formula. Okay, such that for every x, there exists y such that phi of xy, actually, let me write it in the next line. For every x, there is a y such that phi of xy holds. And also, I want to say there is only one y. So for every y prime, if phi of xy prime holds, then y prime is equal to y. Okay, so this is all this is saying is that for every x, there is a unique y such that phi of xy holds. Okay. So this formula phi kind of works like a function. It maps every x to a y, but it's not a function, right? Because remember, in order to define functions, I had to say that this function is a relation, then the relation had to be a subset of some other set that I could define. So here I don't have any of those problems. I'm just talking about a formula. Okay, so a function is a set at the end of the day, but which is like a subset of x times y, its domain times its codomain. But in this case, I'm not talking about a function. I'm just talking about a formula in my language. But this formula has this property that for every x, there is exactly one y such that phi of xy holds. In this case, I call this, what do I call this? A class function, of course. Then phi of xy is called the class function. So it's not a function because, again, it's not between two sets, but it's kind of like the relation that classes had. Okay, so the eighth axiom, which is honestly not that interesting again, is the replacement axiom. And it says this. It says that if I have a class function, so if phi of xy is a class function, and x is a set, big X is a set, then there is a set that contains all the y's corresponding to the x's here. Then there is a set y such that phi, and there is a set y, let's say it like this, containing exactly small y's such that there exists an x phi of xy. Okay, so I'm just saying, suppose I have a set x, and phi is some sort of a formula that has only one solution y for any given x. I can take every member of my set and I can replace it with the corresponding solution in phi, and that would still give me sets. Okay, this is the eighth axiom. Again, you will only see this if you do some more set theory. We're not going to use it in this course. The ninth axiom is kind of interesting. So, yes, it's called the axiom of foundation. Look, so far, our axioms have talked about what we can do. But now we have an axiom that tells us what we cannot do. Okay. So I can use my axiom so far to build a bunch of sets, but there is no axiom that says the sets are only things that can be built using previous axioms. So maybe I have a set that is not created using any of the previous axioms. And I can make really weird sets if I want to allow those things. So here's the axiom of foundation. It says that every set X contains an minimal element. This is the first time when writing formally would be more understandable than writing in English. So what this means is that for every set X, there exists some member Y, so Y is in X, such that X intersection with Y is the empty set. So basically, the problem is this. The problem is that whenever I have a set, I've seen that my sets can contain other sets as elements, right? So suppose that I start with a set X, and then I look at one of its elements. Then I look at an element of that element, and then an element of that element, and so on, and keep going. I don't want to be able to go forever, right? So I want to have a foundation. I want to have a point where I say, well, I cannot open this set anymore. This is the end, right? Okay. So let me, for example, give you a theorem using this axiom of foundation. Okay, actually, another way I can write this is just this, right? So I can say for every set X, there exists some member Y in X, such that for every other member Z of X, Z is not in Y. Okay, this is the same as saying X intersection Y is empty. Okay. So whenever I have a set, I should have an element that doesn't contain other elements of the same set. Because otherwise it seems like I can just keep opening my elements forever. Right. Again, this looks very unintuitive. You don't need to worry about it. Actually, the reason this is Zermelo-Frankel is that Frankel added these weird things. Zermelo didn't have these things, and life was good. So, anyway, I can prove a theorem based on this. And actually, let me just write it here because this is the last axiom I want to talk about today. So I want to say this. I want to say let X be a set. Then X is not a member of X. Okay. Again, one of the reasons we have this axiom is to stop having stupid sets like this, sets that are members of themselves. Right? So why is this the case? What's the problem if X is a member of X? Okay, so I can do this. I can say, let's define a new set. Let big X be a set that has only one element, small x. Okay. Then what's happening here? Every element of big X has intersection with big X, right? Because what is small x intersect with big X? It's just small x, right? So if, okay, I'm doing proof by contradiction, sorry, I forgot to say that. So suppose X is a member of itself. I'm going to define another set, big X, that is just one element, small x, right? And this set, big X, is violating this foundation axiom because it has exactly one element, but its intersection with that one element is not the empty set, it's X. Okay. And of course, I have to check the base case here as well, which is small x cannot be the empty set because the empty set is not a member of itself. Right? Because I want to say this is not the empty set, so I have to make sure here it's not the empty set. It's a stupid corner case. Anyway, the point is that when I have an axiom like this axiom of foundation, this already says that I cannot have weird sets like this, sets that can be basically unpacked forever, sets that are members of themselves. But it also stops us from other weird types of unpackings that go on forever. Okay. Great. So now I want to talk about something else. I want to talk about the sizes of sets, or what we actually call the cardinality of sets. I'm not going to define cardinality first. I'm just going to tell you how you can compare the cardinality or the size of two sets. Okay. So when are two sets the same size? Okay, first of all, can I even define like finite and infinite sets? Yes. So I can have this definition for a finite set. I can say a set X is finite if there is a one-to-one correspondence. So there is a function, let's call it f, from X to one of the natural numbers, right? Such that f is one-to-one and onto. If there is, let's say, a natural number n and a function. Okay. This just captures our normal intuition of what a finite set is, because remember the number n was a set that actually had n elements, right? So if I have another set X, and if this set X is in one-to-one correspondence with a set of size n, then I believe that it has size n. And I can then say it's a finite set. And I mean, in this case, I would just write something like this as well. I would just write that the size or the cardinality of X is just n. Okay. Now this gives us a definition of an infinite set. An infinite set is a set that is not in one-to-one correspondence with a natural number. So easiest definition ever, infinite set. A set X is infinite if X is not finite. Okay. So I already have some intuitive understanding that infinite sets are bigger than finite sets. They have more elements. Right. Also, if I have two finite sets, I have a good intuitive understanding of which one is bigger. I just look at the size or cardinality of each of the sets, and that's a natural number. I know how to compare natural numbers. Right? But how do you compare the size of two infinite sets? So we want a definition of smaller and bigger set that works for both finite and infinite sets. Okay. So here's that definition. So I'm going to say this. I'm going to say, let X and Y be two sets. We write this. X is the same size or same cardinality as Y, or sometimes we write it like this. Size of X or cardinality of X is the same as cardinality of Y. If and only if there is a one-to-one correspondence between these two sets. There is a function that is one-to-one and onto, and it goes from X to Y. Okay. So this is kind of interesting because I'm writing cardinality of X here before even defining what cardinality is. Okay, so if this part doesn't make a lot of sense to you, forget about it. Just think of it like this. I say X is congruent or similar to Y if they're the same size, if I have a one-to-one correspondence between them. Okay. Great. So let's see some things here. First of all, for finite sets, it's pretty obvious. They're the same size if their cardinality is the same natural number n, right? So every set of size 5 is the same, is in one-to-one correspondence to every other set of size 5. Based on this definition, first of all, I want to say that having the same cardinality is kind of like an equivalence relation. Again, it's not exactly an equivalence relation because it's a relation between sets and we don't have a set of all sets. So I can't call it an equivalence relation, but it has properties that are similar to equivalence relations. So for example, I can say that for every set X, X is the same cardinality as itself because I have a function that is one-to-one and onto from X to itself, just the identity function, map every item to itself, right? I can also say this. I can say if X is the same cardinality as Y and Y is the same cardinality as Z, then X is the same cardinality as Z, right? And again, this is for every X, Y, Z. Why? Because I basically have a function F that maps elements of X to elements of Y, and it's one-to-one and onto. I have a function G that maps elements of Y to elements of Z, and it's one-to-one and onto. How do I find a one-to-one and onto function from X to Z? Just do GOF, right? GOF is from X to Z, and it's very easy to prove that it's one-to-one and onto. Okay, because the combination of two one-to-one functions is one-to-one, combination of two onto functions is okay. And of course, I also have the property that for every X and Y, if X is the same cardinality as Y, then y is the same cardinality as x. And here the idea is that I have a one-to-one correspondence from x to y. If I want a one-to-one correspondence from y to x, I can just look at f inverse. Okay. And I'm not going to formally define f inverse. You can easily define it yourself using the axioms we already have. Okay. So great. So if I look at the class of all sets, I can now divide the class of all sets into a bunch of subclasses based on the size or the cardinality of these sets, right? And again, finite sets are no fun. I know everything that I should know about finite sets. I want to see what's fun about infinite sets. Okay. So here's my first theorem. I want to say, let's look at the set of even numbers. So let E be the set of even numbers. Okay. I claim that this set is the same size or the same cardinality as the set of all natural numbers. Okay. So they're both infinite and they're the same size. By the way, mathematicians hate it when I say size instead of cardinality, but I'm a computer scientist, so size. They're the same size. My size can be infinite. Okay. I just have to give you a one-to-one correspondence between these two sets, right? And I can just have a function f. I mean, I can give you a one-to-one correspondence from E to N or from N to E. It doesn't really matter. So I do from N to E. And I just say, take any number N and map it to 2N, right? You can easily check that this is a one-to-one correspondence. So because the set of even numbers is in one-to-one correspondence to the set of natural numbers, they're the same size. Okay. I can say the same thing about the set of odd numbers. The set of odd numbers is the same size as the set of natural numbers. Here's another theorem. Let's say that I look at the set of prime numbers. So let P be the sets of prime numbers. I claim that this set is also the same size as the set of natural. Okay. Why is that the case? Because remember when we were doing in the good old days number theory, we said that there are infinitely many prime numbers, right? So I can just sort my prime numbers. I can say P is this set, is a set consisting of P1, P2, P3, so on, in increasing order, where P1 is less than P2, less than P3, so on. So P1 is 2, P2 is 3, P3 is 5, and so on, right? And now I can have a function. I can have a function f, let's say from P to the natural numbers, which maps every Pi to I. Or I could also do the opposite. I could have a function from natural numbers to prime numbers. It basically maps the number I to the ith prime number. It's one-to-one and onto. So they're the same size. Okay. At this point, you might think that all the infinite sets are the same size. That's not the case, I assure you. We will see something about it soon. But I'm going to show you some more things that are the same size as the set of natural numbers. So here's the other theorem. N times N, which is basically the set of all pairs of natural numbers. That's the same size as natural numbers. Okay. This looks very weird because intuitively you would think that this is a much bigger set than the set of natural numbers, but no, they're the same size. So here's the idea. What are the numbers in N times N? Well, I can just think of them as points, right? I have 0, 0, 0, 1, 0, 2, 0, 3, so on. And then I have like 1, 0, 1, 1, 1, 2, 1, 3, and so on. And let's just continue like this. I have all these points. And what do I want to do? I want to find a function that maps each of these points to a number. And I want that function to be one-to-one and onto. Okay. So here's the thing. If I start numbering like this, if I say this is 1, this is 2, this is 3, 4, so on, keep going, I will only number the first row. So that's not good, because then it's not even a function, right? So I want it to be a function, and I want it to be one-to-one and onto. So the idea is this. I'm going to number them like this. Okay. Or I could also do it the other way, right? So I'm going to do this. I'm going to say, well, let's first look at this diagonal. Let's give this number 1. Let's then look at this one, give it numbers 2 and 3. Then look at the next one, give it numbers 4, 5, and 6, and so on. Right. So I will assign a number to every point here. And you can check that this is one-to-one and onto. Every point is getting exactly one number. Every number is getting exactly 1 point. So this is a one-to-one correspondence between the set of pairs of natural numbers and the set of natural numbers. So they're the same size. Okay. Great. But could I do this in a different way? So suppose that instead of saying that the sizes are equal, I want to have a way of saying that one set is smaller than another set, right? So I can have another definition here. When can I write that a set X is smaller than or equal to a set Y in terms of its size, in terms of its coordinate? I can do this whenever I have a function from X to Y that is one-to-one. If it's not onto, it's mapping every element of X to some element of Y, right? But it's not covering all of Y. So intuitively, I would think that X is a smaller set than Y. So we write that X is less than or equal to Y if there exists a function that is one-to-one. So if there exists a one-to-one function f from X to Y. Okay. Of course, by this definition, if two sets are the same size, then each of them is less than or equal to the other one, because I have a one-to-one and onto function between them. So I have a one-to-one function from each of them to the other, right? But I can easily prove this theorem. I can prove that n times n is actually smaller than n, smaller than or equal to. What does this mean? This means that I should just give you a function f from n times n to n. And I have to make sure that this function is one-to-one. So I'm just giving you a function that's mapping pairs of natural numbers or points to natural numbers. And I want to make sure that this function is one-to-one. Well, here's one example. Suppose I have the pair xy. I can just map it to 2 to the power of x times 3 to the power of y. Right? I'm not using all of my natural numbers, but this is definitely a one-to-one function, right? Because we had uniqueness of factorization. Okay, great. So you see that it's actually not that weird that n times n is smaller than n, smaller than or equal. Right. But I can go even further than this. Here's another theorem. I want to say that for every natural number k, n to the power of k, so the set of tuples of k natural numbers, this is the same size as n. Okay. Now, again, I can do something similar to this one to just create it, right? So I can say, for example, in 3D, I have 3D points. I'm going to, again, cut them diagonally with a bunch of like planes, and then number in each plane first and go forward. And generally, I can do this for every k. But another way of looking at this is this. I can take n to the power of k. What is this? This is just the set of all x1, x2 to xk's, such that every xi is in n, right? So it's a set of k tuples of natural numbers, right? I can break these k tuples down by their sum, okay? So I can say, for example, the set A0 is the set of all k tuples, x1 to xk's, in n to the power of k, such that the sum of the xi's is 0, right? So this A0 is going to only have the 0 point, the origin, right? So this is a set with only one element, 0, 0, right? But then I can say A1 is the set x1 to xk of all the tuples, such that the sum of their coefficients is 1, right? So this is the set that contains 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, blah, blah. Okay, but this is a finite set, right? Generally, I can say AI is the set, well, and I have already used I. I can say AJ is the set of x1 to xk's, such that the sum of the coefficients is j, right? And this is going to be a finite set. So I took the set n to the power of k, which is the set of all k tuples, and I divided it into a bunch of finite sets. Now, when I want to assign numbers to elements, I first start with the elements in A0. I assign 1 to this, and then I assign 2 to this, 3 to this, and so on. So I'll just assign numbers to elements in A0 first, then I assign numbers to elements in A1, then I assign numbers to elements in A2, and so on. So every element will get a unique number, and every number is assigned to a unique element. So this is a one-to-one correspondence. So generally, what I'm doing here is called counting. And a set is countable. A set X is countable if it has the same size as the set of natural numbers. And what I've shown you so far is that these sets are countable. So the set of even numbers, the set of odd numbers, the set of prime numbers, and the set of pairs of natural numbers, the set of k tuples of natural numbers, these are all countable. And I mean, the name makes sense because basically when I say a set is countable, it means that I can count its elements. I can have a function that assigns a natural number to every element, and it's going to be one-to-one unknown.